I remember my instructor for structural design course once mentioned it, and that always I carry that particular advice with me always. Design codes are legal documents, but they should be written in such an unambiguous manner that it can be interpreted and implemented correctly by a graduate engineer. Right? A BE civil engineering is supposed to read all the codes relevant to civil engineering profession and understand them and implement it correctly. Unfortunately, the development in recent times has been violating these basic guiding principles of code writing. 1893 has grown into such a monstrous entity. I wonder if the people who are approving in that CED 39, those who are approving that code, they themselves understand what is going into that. There is a reason for that, because the people who are approving that CED 39 members have really no stake. I mean, that is a problem with the structure that we have in BIS. I mean, please take it with you. And I have stopped attending BIS meetings since more than 20 years. Last meeting I attended was maybe 2008 or so. After that, I have never attended any BIS meeting. I mean, you can imagine the kind of experience I have had to cut myself so clean. So the problem is, these committees wield enormous power. Their word is law of the land. But the members of that committee have zero accountability to what they are writing. When 1893 2002 came out, that was a major revision in format, changing the format from 1984. Lots of things had happened, and 2002 it was made into a new format. But in the process of doing that, we messed with several structures other than buildings, to the extent that we still do not have a design code for concrete gravity dams. I mean, complete mess. Now the problem is, at that time, 2002, you would recall, if you compare 1984 version with 2002 version, you will find that Southern Peninsula was in Zone 1, and in 2002 it was raised to Zone 2. Now it is once I was attending a workshop at IIT Madras, and I was discussing with colleagues there. I said, I mean, it is a good fortune that insurance is not a very standard practice in our country. People do not buy insurance. Buying earthquake insurance is a very, very low business proposition. But if that was the case, I mean, fortunately, Southern Peninsula, nobody even talks about earthquake, forget about buying earthquake insurance. But if this was to happen in northern parts, what is the problem? Insurance companies do not decide about tariffs by doing a rigorous analysis. It's not possible. Their guideline everywhere in the world is the design compliant with the code of practice? If it is, this is the tariff, right? This is the premium that you need to pay. If it is not compliant with code, you pay higher premium. That higher premium could be anything. Now the point is that I want to bring to your attention, Till the 2002 code was issued, one day before that, all the buildings in Chennai and Southern Peninsula were compliant with code. And when the 2002 code came into being, all of these buildings, existing building stock, became deficient. Right? Now, if you have to pay for lower insurance premium, then you need to upgrade your buildings, right? Retrofit them. Now, who pays for the retrofit? The building owner will claim, when I designed it according to the codes. You decide to change the code, what is my fault? Right? If it has to come to the standard, better government shells out money to make it safe environment for the public safety, in the name of public safety. Now the problem has gotten worse and worse. Just now Mr. Prasad was showing that you have a huge red band in the Himalayan belt. That's problem is aggravated several times, and that violates another cardinal principle of code. I will come to that. There are several problems with that, and please pardon, I mean, this is a very harsh critique, may not, I mean, you are the sole representative of BIS, so that will be a barrage. Please pardon. So, first of all, the historical context. Shelter, need of shelter is as ancient as the civilization. So, safety, concept of safe shelter also evolved along with civilization. And of course, there were rules and regulations to drive, I mean, otherwise, I mean, there were corrupt people even in ancient times, there are corrupt people even in today's times, right? So in order to check the malpractices, certain rules and regulations were required, and that have always been the case. The oldest surviving set of rules for building codes is the Hammurabi, Code of Hammurabi. There are, I mean, Hammurabi was a king in Babylonia. That's more than 3,000 years old. These are edicts which are etched in a slate, stone slate. And that slate is now preserved in Louvre Museum in Paris. So, very simply, Code of Hammurabi, it's like, these are like an eye for an eye kind of jurisdiction. If a builder build a house for someone and construct it properly, and the house which he built fall in and kill its owner, then that builder shall be put to death. Simple. Right? So like for like. So if it kill the son of the owner, son of the builder shall be put to death. If it kill a slave of the owner, that's the time when slavery was rampant. It was an accepted practice. If it kill a slave of the owner, then the builder shall pay slave for slave. The slave of the builder will be given to the owner, owner of the house. And if it ruins goods, what Mr. Prasad was referring to as non-structural elements. So the concept of non-structural elements goes way back, right? That's, I mean, a house, safe shelter is made to store valuables, which needs protection, right? So that value of those goods may be more than the cost of the shelter itself, right? So if it ruins goods, he shall make compensation for all that has been ruined. So essentially saying builder will go bankrupt. जितना कमाया नहीं उससे ज़्यादा तो देना पड़ा. And so, and then if the builder, whatever he builds, if it sustains damage, that damage will have to repair without any compensation in return. So fairly straightforward, and these are the first known codes for structural design and performance that still have survived through antiquity. This is not to say that there were no such guidelines before that, but these are the oldest that have survived to this date. So how do we evolve? How does the structural design has evolved? As I said, need of shelter is as old as the civilization itself. And in the ancient times, since the time of caveman, these shelters were designed and constructed by craftsmen, experienced craftsmen, by trial and error. And through that process of trial and error, they evolved certain principles of practice, trade practices, trade secrets, if you may call so, right? Today we call them as rules of thumbs. And those were primarily based on geometric proportion. One such rule of thumb is still used for the design of concrete gravity dams. In spite of all that sophistication you have, still that rule of thumb based on geometry is used for the design of concrete gravity dams, which is the resultant of all forces acting on the dam cross section shall not pass beyond middle third. If it passes within middle third, there is no tension anywhere. Right? Simple geometry. So with the advancement, those are geometrical, earlier times, the material of construction was primarily stone. So as long as stone is very, very strong in compression, they have survived millions of years putting through that self weight of so many layers. So stone is typically, particularly the kind of stone that we use in construction, they are very, very strong in compression. So structural forms evolved how to transfer everything into compression. They tried several times, they failed. Little tension, everything falls apart. So then the geometry evolved how to transfer, how to develop suitable structural forms where everything eventually ends up as a compression. That's how the arches evolved. That's how our aqueduct on Solani River was built. It's beautiful brick masonry arch. Right? So everything is with compression. And in these constructions, the geometry was very, very important because material, not enough was known about the theory of elasticity and other stress analysis. So typically it was rules of thumb. If this is the span of the arch, height has to be this much. Generally they started with a semicircular arch, and gradually as the confidence grew, they started making it low height, as tried with lowering the height until they find that it is quite safe if height is kept not less than 1/3 of the span. But then the abutment has to be very, very strong to take care of the thrust, because then the force is not vertical, it is horizontal. So that has to be taken care of. So gradually, as the confidence experience grew, these rules of thumb evolved, and with the advancement in science, as more refined theories were developed, theory of elasticity. I mean, 17th century Europe was buzzing with activity in theory of elasticity, and then plasticity followed. And then people started looking at how these rules of thumbs can be provided some rational basis. Can we have some basis for that? And rules of thumb are not really very good way to, or not very honorable way of designing anything. So then when they developed, tried to put together, then they came up with, that is what led to different formats of code. So started with permissible stress or working stress. So just translate whatever was the current practice, socially accepted norm, because whatever the structure was built according to the accepted norms of the practitioners of the day, society has accepted whatever safety was built into that. Of course, nothing is 100% proof. If anything man-made will fail at some point or the other. So whatever you build, there is a safety margin. So whatever safety margin was there in the structures built according to that, society had accepted that. So there is no point and there is no rationale to change that safety margin. The only point was how to ascertain what was the safety margin, to get more comfortable with the newer materials that were coming up with higher load carrying capacity. So that will allow, if you can have some way to figure out what is the safety margin in these kind of constructions, historical constructions, we can work according to that and develop design methods for working with new materials and new structure, experiment with new structural forms, right? So that's how working stress method developed. Then it was soon realized that working stress method, I mean, which safety are we talking about? There are so many different modes of failures. So factor of safety changes with one mode of failure to another mode of failure. So what are we talking about? Right? So then it came to, and then another problem was we are not really using the material efficiently. Right? Permissible stress, using that is, it is like you may understand, appreciate this a little better. Permissible stress in a bar of steel or truss member under compression, there is an allowable stress, right, which is obviously not related to yield stress. It is related to the buckling load, right? Now that buckling load, actual buckling load, will depend on what are the end conditions and what are the geometric properties and so on, right? But the code specifies certain value, so that you work out a design satisfying that permissible value without knowing what is the safety of refractive, what is the critical stress value for this system that you are designing, and how it will actually be translated, that's another story. Right? You are still working only on paper. Civil engineers do not have luxury of prototype testing like other fields in science have. Right? You develop a theory, you can test it, ad infinitum and refine it. We don't have that luxury. It's one and done. Right? So the point is, the factor of safety itself is unknown. So lots of, you may be happy. I mean, it's like ignorance is bliss. If you just don't go beyond what is written in the code without trying to read between the lines, you are happy, oh, I have followed the code, forget about it. But then once you understand, think about it little more deeply, I mean, that permissible stress, what is the critical stress from which it has been derived? You don't know that. Because that critical value depends on so many things which are unknown. Right? And then these kind of uncertainties of permissible stress first led to ultimate load analysis, where you knew what is the ultimate load carrying capacity, and then you bring it down to working levels of loads for design that you design for. You will limit the loading in this to this limit. Again, it changed only, that's only a cosmetic change, nothing really happened. It's still working with allowable stress. And then sometime in early 20th century, limit state method was developed. I didn't know until recently that it was developed in Russia. Russians don't get as much credit for technological innovations. Now, that's a major advancement, and we still adopt that, so much so that some of the fields still have not really migrated to limit state method. Geotechnical engineering is one. I mean, all of them, geotechnical engineers are happy still with working stress. Very little is done in limit state, if at all. So, but there is a reason for that. But let Ritesh deal with that. So now, the design is essentially, what are we designing? When we look at structural design problem, client only has certain vague idea about what is required. Before you come to design, you need to decide about the structural form. What type of structural form will be suited for the desired requirements, right? And once you have decided about the structural form, you come to the design. Now, when you come to design, obviously this safety measure and safe design, all this requires what? Analysis, right? How do you ascertain the safety eventually? Analysis. So what analysis? There are three types of analysis. Analysis has three segments. Unfortunately, most of the people are not aware of the three, all three. First one is the load analysis. Analysis of what loads are going to come onto structure, or what the structure is supposed to support. That itself is an analysis. Second one is analysis of response of the structure to the applied load, right? And third is the safety analysis. How far is the response away from the failure? So what is the safety margin, right? Unfortunately, first and third are very conveniently ignored. Last 100 years have been devoted only to the response. And to that, I have this submission. It is useless to seek extraordinary high degree of precision in response analysis if the load and safety criteria are not well defined. If there is 100% uncertainty in the load, what am I gaining by improving 5% accuracy in the analysis? right? This actually uh, reminds me of one discussion I was having with one of my friends at IIT Kanpur. I was on the verge of submitting my thesis, and that friend was about to leave for PhD in Berkeley. So he asked me, Manish, क्या है यानी PhD process कैसा होता है क्या होता है? So as you grow through the PhD process, through all the trials and tribulations, you become wiser and you become mellowed down, right? So then I told him, I mean, I was one part of my PhD thesis was for development of some analysis in random vibration framework for phenomena which is evolutionary in nature, which is not stationary. Statistical characteristics are not stationary over time, so they are changing with time. So, but if you look at it, it's an analysis problem. So I was just, I just said कि यार पता नहीं 100 साल हो गए हम अभी भी एनालिसिस पे ही रुके हुए हैं. All that I've done is just another way of computing another set of numbers. Who knows what? So that's the problem with the wrong emphasis we have in our approach. That's entire system of university setup is geared like that. But that is something that one should be aware of, not to fall into the trap of these marginal apparent improvements which actually make no difference at all to the professional development, right? So analysis of loads, I mean, how do we design any system? How do we apply loads? 875, right? IS 875 that gives you all those load parameters. Have you ever, load parameters are given in the form of surface area, so many intensity per square meter. Have you ever witnessed a situation where the load is distributed like surface area? Never. That's all equivalent uniformly distributed load. That's another level of covering up things, right? And analysis of that, even if it is equivalent uniformly distributed load, how do you get that number? How do you arrive at that particular number? You need to do very serious surveys. It's a very costly affair. I am not aware of when the last survey was done. So how are these numbers coming up? Right? So that's something I'll come back again. And then, what is the safety margin? How do I say this much safe is safe enough for me? What is your notion of safety? And does the notion of safety also entail uniformity across the globe? Is the notion of safety same in India, in Pakistan, in Nepal, in America? Because, see, as I take you from historical times to present times, codes maybe with the format of the code, but we are not changing the safety. We should not, because society has already accepted certain level of safety. If I change that safety, I am not doing justice, and there is no basis for changing the safety. I don't need to arbitrarily increase the safety margin unless there has been a catastrophe somewhere. Right? So unless there has been a catastrophe, why should I increase the force level? Question number 1 for this revision of 1893. Why the forces in the Himalayan belt have increased? There has not been any damage in any earthquake. Even Bhuj, in the epicenter, right in the epicenter, not a single CPWD building developed one crack. All CPWD buildings survived that earthquake. So what is the basis of increasing the forces? And that level of force to which they are increasing, that's another story. I'll come to that. So I'm given half an hour, but please pardon. I mean, this is quite an emotional topic, and I do get carried away at times. So please tell me when to stop. गुरुजी सामने हैं, मैं उनका समय निकालना चाहता हूँ.
You continue, right? This is giving good ideas.
So no use of extraordinary high precision, although I claim to be an expert in finite element method and nothing can be as precise as finite element method, but knowing what you are doing and within the parameters is always a good thing. Too much of everything is bad. So legal implications of code. Codes are legally and ethically considered to be the minimum criteria that must be met by the design and construction community. Right? That's a minimum. And that is why it is all the more important that it should not be increased. Code level prescriptions should not be increased without justification. If anybody wants to have a higher degree of safety, they are always welcome. Right? So that's only a minimum level that is being specified. Basis of building code development is to safeguard the health, safety and welfare of the public. First and foremost goal of building codes is the protection of human life. I'm emphasizing here human life. That's life safety is the basic objective, and then comes the economic. Right? So life safety is one, and then we come to economic performance and subsequent economic losses. And then there are two kinds of provisions in the code. Prescriptive provisions and performative codes. So prescriptive provisions, they just tell you, do this, period. You don't have any choice. For example, I hope that number is still the same, 13920, the ductile detailing, right? So there is a certain regions where the spacing and lateral ties have to provide higher confinement. It should not exceed that limit. So the idea is derived from experimental observations that if you do this, then confinement improves the ductility, and you just hope that if I do this, the entire structure will somehow become more ductile. The experiments are done on members. Experiments have never been done on the whole structure. But then, as the structure is sum of individual parts, and if we have seen this in part, we just hope that the structure will also behave in the similar way, if not exactly same way. So that's a prescriptive, right? Nobody has known, and this ductile detailing has an effect on the use of your response reduction factor, right? So roughly, I mean, as a rough figure, response reduction factor of 5 for specially ductile moment resistant frame, you would assume ductility is 5. That's just assumed value. Nobody has ever tested the full structure and evaluated what is the actual ductility of the structure. Right? We just assume that it is something that we should expect. Nobody knows. Fortunately, no such structure has ever given us any opportunity to experimentally evaluate ductility in field. And then there are performance codes which just define the problem and let the designer take call. Whatever solution addresses this problem, that's fine. And there are criteria how to evaluate that performance criteria. Whatever you do, as long as this performance criteria is met, you are good. Right? So these are the two kinds of provisions that are typically used in design codes. So I was referring to the human safety, life safety. Look at this map carefully. Colorful map, but those colors are representative of the inequalities in society. Colors indicate per capita expenditure on health care in different countries. Right? India is just second from the bottom, between $50 to $99 per person per year. And this is 2017 data published in 2019 report of WHO. So what does this imply? I mean, there are several other statistics. I have a similar figure about the accidents, number of fatalities in road accidents, and how that varies with GDP of the country. You will find that high GDP nations have very low accident fatalities. Low GDP nation will have very, very high accident fatalities. Right? So what does that mean? The concept of safety that I was referring to, lower level of safety is accepted by poor countries, developing countries, underdeveloped countries compared to developed nations. Right? Of course, everybody should aspire to become developed. If somebody is underdeveloped, does not mean that you should remain underdeveloped. But then, in order to go to that developed stage, you need resources. Do you have that wherewithal to spend whatever meager resources you have on just show off? And that is what I will come to this. I'm using this word very carefully, show off. So, different countries have different capacity to spend. And that, of course, governs the cost of living also. You will find that wherever per capita expenditure is low, you will find that cost of living is also low. And everything is low. So don't compare this in absolute numbers. It's not that life in India is so bad to be figuring on the bottom, I mean second on at the bottom, right? It's just that cost of living is low, so the absolute terms per capita expenditure also works out to be low, right? Healthcare in United States is nothing to be proud of, right? But still they spend the maximum. But then road fatality rate in United States is very small compared to road fatality on Indian roads. So that's just to bring out the differences in the acceptable risk or safety, the levels of safety, whether it is acceptable or whether it has been accepted by the society. These two are two different things. What is acceptable to society is one thing, what society is forced to accept is another thing, right? Distinguishing between them is very, very difficult and not really an engineer's job, right? That's beyond engineering domain. But one should be aware of that. And that's only a working approximation. Whatever the society is living with is fine with it. May or may not be true, but that's a good first order working assumption that whatever is currently prevailing, that is the acceptable source, condition. And coming to that safety, the design, objective of the design is to provide a safe shelter at the minimum cost to the owner, right? That's another, that line I borrowed from my instructor, my teacher. He very casually once said, a design course, भाई इंजीनियर तो बढ़िया होता है, बिल्डिंग तो कोई भी बना दे, देयर इज सो लार्ज फैक्टर ऑफ सेफ्टी, उसमें क्या कोई भी बना दे. The importance of engineer is in providing solution at the minimum cost, right? So wherever you can save money, you should, right? But not at the risk of safety. You should know where there is a possibility of saving and where you should be prudent and not cut down on material or other resources, right? So the bottom line is cost, total cost of ownership of the structure should be minimum, and yet it should be safe. What are the conditions? How do we ascertain safety? Present day limit state method. Just work out the strength criteria. Factored capacities should be greater than factored load effects, right? So phi r should be greater than gamma L. I combined everything into just these two terms. Phi and gamma are the partial factors. R and L are representative of the capacities, resistance, and the loads. Several different loads can be combined, and accordingly you will have different partial factors. You must have used these partial factors. Where do they come from? One 1.1, 1.3, 1.2. I mean, when I was an undergraduate student, they seemed like magic numbers. पता नहीं क्या है, ठीक है, जो भी है, खत्म करो, कैलकुलेट करो, डिजाइन करो, एग्जाम पास हो गया, खत्म हो गया, ठीक है. But really, where do they come from? And now I come to the question, why I stopped attending BIS meetings. these partial factors or similar factors are just decided, अरे अमेरिकन कोड में ये है, यूरो कोड में ये है, एवरेज करके हम इंडियन कोड में डाल दें. That's the way those meetings proceed, right? And we believe them like gospel truth. Right? But then, and that's why I am very, very critical of that, people sitting on those committees do not realize or they do not want to understand what they are doing is a crime. They have enormous power without any responsibility. Nobody can, if something happens, nobody, not a single member of that committee is going to face any consequence. Right? So, I'll tell you how it comes, and that is an advertisement for elective course that I'm offering next semester. How these factors are arrived at. So, as I said, the responsibility of the designer is to provide a solution at the minimum cost. So what is the cost breakup? There is a capital expenditure at the first instance, right? CapEx. And then there is some recurring maintenance cost. And then in the event of failure, there may be major repair and also compensation to be paid. Right? Now, just imagine the situation. Is maintenance cost in India very high or of the same level as that in America? Is the repair cost in India of the same level as that in America? No. Cost of living is very low. Everything is cheap here. That is the reason why we still using reinforced concrete, not move to steel structures. Labor is cheap. We can produce reasonably good concrete even with manual mixing. Right? So the point is, this cost breakup is very different in different parts of the world. And these components will be different. I mean, capex will increase if I design it for higher intensity loading. It will decrease if I design it for lower intensity loading. Simple si baat hai. Right? So I can choose to design, if my maintenance and repair costs are going to be very small, I can afford to take a call to design it for a lower level at the first instance, incur lower capital expenditure, and then maybe distribute the maintenance cost over the service life, and then if खुदा ना खास्ता कुछ हो गया, repair भी देख लेंगे. That's again a probability, not most of the structures serve their design life without ever experiencing earthquakes. Right? So these components, and that's what I try to emphasize here, are strongly coupled with socio-economic factors of a community. High safety and low cost are in general conflicting requirements. And a judicious trade-off is required based on your considerations. So for example, if it is a developing country where repair and maintenance costs are going to be very small, why should I adopt the design standards of America? Why should I not be designing for lower level of forces and then offset the costs over a period of time in maintenance? Right? But no. ATC 3, Applied Technology Council, third report in 1976, defined that America, California, actually only for California, okay, they just decided, that committee decided some number, okay, seismic hazard for design, we should use this value is good enough. That was a committee decision, that's fair enough. Based on their professional experience, they decide. It so happened that two people in United States Geological Survey, Algermissen and Perkins, developed first probabilistic seismic hazard map for the United States. And the number that the committee recommended was very close to what Algermissen and Perkins quoted as 475-year return period earthquake. And that 475-year return period earthquake, they also, they could have computed it for anything. They just computed because that corresponds to using Poisson distribution model. That's also questionable. Poisson distribution itself is questionable assumption, but nevertheless. 10% probability of accidents in 50 years corresponds to 475-year return period. Now 10%, where did this figure come from? Oh, 10% significance level is used for hypothesis testing, so it was a good number. We just use that. 50 years, reasonable exposure period for a building, 50 years. So nice round figure. So 10% in 50 years, 475. And it so happened that that number was very close to what this group of people in Applied Technology Council had recommended, and that's how 475-year became the design earthquake worldwide. Nobody ever thinks about rationality of this assumption. And there is a difference in the calculation also. I will not get into the problem of fixing upper bound of probabilistic seismic hazard assessment. That's another point of conflict. Algermissen and Perkins, they just use the median estimates without any measure of spread. Any probability distribution will have some spread, right? So Algermissen and Perkins report only talked about what you get by median estimate. And that estimate was in reasonable agreement with the numbers that ATC committee had recommended. So 475-year came into picture. Now people have picked up, nobody has the patience to go through the history and look into how this has happened. Now they have, we are scientists, we like to see our name in print, right? तो कुछ तो अलग करना है, तो क्या अलग करना है भाई? अल्जरमिसन परकिंस ने तो मीडियन लेके कर दिया, अब हम इसमें स्टैंडर्ड डिविएशन ऐड कर देते हैं. ठीक है, प्रोबेबिलिटी मॉडल है, इसका स्टैंडर्ड डिविएशन ऐड कर देते हैं. So now if you add the standard deviation, the immediate question comes, it's a log normal distribution, infinite. You can theoretically go to, how many standard deviations are you willing to take? If you take 1 standard deviation, 2 standard deviation, 3 standard deviation, your estimate of hazard for the same 475-year, the 475-year return period, no basis, just because America is doing, you do that, doesn't make sense from socioeconomic basis. And even in America, original correspondence was for committee recommendation, practitioner's recommendation, rule of thumb translated into some mathematical respectable formulation. And that was done for a particular set of parameters, particular way of analysis. That analysis has been completely thrown to the dustbin. You try to become more kind of, जितना complicate करोगे उतना collar ऊंची करने क्या, right? I mean, what is the fun if you understand whatever I say, right? My prestige as a professor in IIT is only when you don't understand what I say. Right? So that's my problem. So reducing the design load might lower the initial capital expenditure with a higher chance of increasing the other two cost elements, and that is how you should do. And eventually, as I said, advertisement for my course next semester. This is done as a optimization problem. You solve this optimization problem, work out the implications of various design alternatives, and work out which combination of these three costs will give you the minimum total cost. There are several ways of formulating it. I write it in terms of cost. It can also be formulated in terms of utility theory, maximizing the utility of a facility, and so on. So it's same thing with different names. But that's the way to go about it. But it's a serious work, right? It's a serious work. Who wants to do a serious work when just averaging 2 national codes is acceptable? That's the state of affairs at BIS committees, and all done by IIT professors mostly. So now we come to this problem. Lot of buzz about performance-based design. So earthquake, so far whatever I have said is valid for structural design in general. Now I come to earthquake engineering per se. Special problem with earthquake engineering is earthquakes come in all shapes and sizes, right? It's not like one number from that I can pick up from IS 875 and work out the numbers. I don't have any control which earthquake will choose to visit me, right? So I need to take a very prudent decision. So dual level design has been followed for a long time, that no damage in frequent earthquakes, slight damage in moderate earthquakes, and no collapse in severe. Right? So if you design for slight damage in moderate earthquakes, no damage in frequent earthquake is automatically taken care of. So that is how that response reduction factor and all they allow. So moderate damage by accounting for the ductility when that event actually moderate earthquake does happen. Now performance-based design, that dual level design of life safety doesn't really protect your economic losses. It provides safety against death, life is safe, and that has been proved in several earthquakes that our existing codes are good enough for life safety provisions. And that is why it brings more into question why the need to revise the force level unnecessarily. They have proved themselves. Magnitude 7, epicentral region, not a single CPWD building survived, witnessed any damage. So, the problem is, different types of earthquakes, I can't expect structures to perform uniformly, in the same way for different intensities of earthquakes. So now, because if I have to, with the economy shifting from industrial to knowledge-based economy, so even downtime is very, very expensive. You can't afford most of the buildings that we were earlier happy with sustaining some damage. ठीक है, evacuate करके repair करके फिर use कर लेंगे. That is no longer possible. That has a major repercussions on the downside. Economic losses are huge. So that's how different performance levels are now being described, worked out, and that is essentially to limit the damage. So different earthquakes, you try to prescribe what is the damage, that what kind of performance, structural performance you are expecting, right? So it is no longer limited to just the capacities or the resistance exceeding the capacities, factored resistance exceeding the factored capacities. Now damage is essentially a displacement based phenomena. So you are trying to limit the damage. So different damage control measures are prescribed. Ideally, that is how it should be done. So for increasing level of earthquake, you prescribe, and then there are different grades of structures, important structures. You want them to be functional even during severe earthquakes. So how do you define that? So you define lower drift or lower damage for larger earthquake. So that is what the first curve actually shows. That's what we call as performance matrix. So as the structure becomes, importance of the structure increases, what you should actually be aiming for is reduced drift or reduced damage. So on the horizontal axis, these are performance levels. So essentially you may call them as drift measures. And on the vertical axis, these are the earthquakes, intensities of earthquakes. So for important structure, you try to reduce the drift for different intensities of earthquakes. That is how performance-based design should actually happen in practice. But the codes, because we are very, very resistant to change, humans by design, they are very averse to changing anything. They have some comfort zone, very difficult to get them out of that comfort zone. So we know a structural designer knows one way of designing structures, right? So making that designer to adopt a new way of designing is too much. There is stiff resistance. So what is done is, okay, fine, you know how to design for the force. What is typical way, standard way of designing structure? We design for force, strength-based criteria, and then check for serviceability, right? That is how we do. So we do that. Now what we do, in order to achieve that lower drift for important structure, we increase, instead of lowering drift, we increase the load. Okay, for important structure, you design for the same drift limitation that has been prescribed, but you take the higher load, right? That is what is happening on the second figure. So that is the essence of what you call as importance factor. That is what that importance factor is doing. So it is trying to approximately get to the drift limitation by actually imposing smaller drift, whatever drift criteria is there in the code, for higher level of loads, right? Not really the way it was envisaged, but that's a very efficient middle path between theory and practice. Now the challenge is to define the earthquake levels. This problem I just described. I mean, 475 to 475, what is the basis? Well, the borrowed numbers from America. Not relevant for India. Not relevant for anywhere in the world except America. Still, the whole world is blind to that. And it's not just Indian Bureau of Indian Standards. The entire world uses 475 and 2475. Because doing anything else requires too much of work. Right? It is easy for me to say that it is solved through an optimization problem, but that formulation of that optimization problem and getting that formulation, what is that really the correct formulation? The costing, what are the implications of repairs? Some damage happened, then what is the repair cost of that? That is based on assumption. So total cost optimization result is very crucially dependent on what assumed costs I consider in my analysis. Right? One indication is, of course, the problem of compensation. That's a major problem there. If somebody dies, if the building suffers damage, somebody dies because of that during an earthquake. So how do you pose that problem? Assigning value to a human life is ethically impossible, not correct. How do I define that? Oh, somebody dies, 2 lakh rupees laga do. It's not correct. But then you need to swallow that bitter pill and still work out some way to come up with that number. And that is always questionable. The moment I assume some number, it is very easy to question. The reviewer will simply ask, what is the basis of this assumption? And if I cannot defend that, all subsequent analysis is useless. Right? So while it is easy for me to say, and that is why there is a reason why everybody is blindly following 475 to 475, जब तक किसी को समझ में नहीं आता चलने दो गाड़ी.
So can I please in 5 minutes?
Yes. जब बोलो बंद कर देते हैं. ठीक है. So the whole point is we are moving to a society or to situation performance-based design where drift and damage control is the major concern. And today, this 475 to 475 is actually immaterial. Today we have technologies which will allow you to build structures which will not sustain any damage whatsoever, no matter what kind of earthquakes happen. Right? I will just take liberty of showing you 2 examples that we have developed in our department. Oh, okay. What you see here, these are mass blocks and these are leaf springs that you see. So together they constitute spring mass system. Now this mass and spring stiffness is adjusted such that natural frequency of these blocks is 90% of the natural frequency of this primary host. And when I do this, the drift in the primary structure is reduced by 50%. Right? So that is essentially what is required. Now, this is what you see. Tune mass dampers are 100-year-old technology. What I am showing here is distributed tune mass dampers which can be distributed over height. It is not a pendulum suspending, it is just a set of blocks, masses, resting on the roof or floor, cover it with false flooring, use the floor as you will. And this can be distributed over height and the entire system can be, this entire system can be accommodated within a depth of 4 inches. So very, very easy to use in retrofit. And the other one I will show. This is our shock table facility. What you see here, these are concrete blocks interlocked using shear keys. Shear keys made from ply part of the car tire. Right? There is no mortar, nothing. So it is just blocks assembled like Lego toys blocks. And this doesn't fail. We exhausted our capacity of our test facility. Doesn't fail. After earthquake, some blocks get dislodged. Just take it out, assemble it again, and you are ready to go. Right? So what you learn or people talk about, it is not possible to design earthquake-proof buildings. They are lying. We have technology to design earthquake-proof buildings. Thank you. बस हो गया, लास्ट स्लाइड थी. थैंक यू.